All right, guys, so back from the slight interruption from Zoom. So as I was saying just now, is that angles that are formed in the same segment, they are equal. So if you notice these two angles, they are formed on the arc of the arc above A and B. That section of the circumference above A and B, that's where these angles are formed. So one is formed at X on the arc above A and B. This one is formed at Y on the arc above A and B. Now, the word subtend simply means form. So the angle subtend at X, so it forms at X. From A to B, from A to X to B, so the angle forms at X. From A to Y to B, the angle forms at Y. Now, the thing is that these two angles are subtend on the same arc, or the same segment of this circumference. So that's why they say angle formed within the same segments will be equal, right? So once they're coming from the same points, A and B, now sometimes they will give you a card from A to B, which is a straight line. But there are times when there's no line at all, but the rule still remains. Once you're using A and B without the card, once you form it in the segment above A and B, they're in the same segment. And once you form it in the segment below, they are in the same segment. So if you imagine that you erase the dotted line, these two would be still in the same segment. Now, if you form any below A and B, any angle below A and B, then now you are forming these angles in this segment below A and B. And any two angles or three or four, no matter how many angles you form within a segment, all of the angles that form on the circumference within the segment will all be the same in terms of angle, in terms of their size. All right. So this angle down here, if you call it Y, it will be the same as this angle over here, which is also Y. So wherever they form within the same segment, they're all going to measure the same in terms of the size of their angles. So if you even form it here, and then move it back to B, so both are going from A to B. So this angle here on this section, at this point on the circumference, will also be equal to Y. And so that's what the theorem is saying. Now, if you should go back into the major segments and form more angles from A to B, then the angles in the same segment are going to be equal to the same. So this angle here also going to be equal to X. All right, so that's a theorem. Is everybody clear on the theorem now? Raise your hand, guys. Are you good, Miss Green, Miss Waysome, Miss Doherty? Are you hearing me?
Yes, sir, I'm clear.
Okay.
Yes, sir.
All right, so that's for that theorem. Now, this is theorem 8. Now, if you are forming an angle within a segment, So if you imagine that there was a straight line from A to B, right? Imagine that there was a line from A to B. Sorry, not B, but from A to C. Then this line would be a chord from which A and C, from which they are forming an angle within the segment of B. Right? So from the chord AC, you're forming an angle in the segment of B. Now, this theorem says that the angle that is formed within the segment given your X is half the angle that is formed at the center from the same 2 points AC. Now, so that's a theorem. Whatever angle is formed at the center is twice the angle that is formed within the segment opposite to the angle here at the center. Or if you think in terms of, if you're thinking in terms of sectors, anybody remember what sectors are? Anybody remember what sectors are? Guys, how many sectors is this circle cut into? How many sectors do we have here? Anybody? Please, somebody respond. Miss Green, what is a sector? Miss Waysome, what's a sector? Miss Dorothy, what is a sector?
So exactly when you're cutting up something in small parts.
Not just small parts. Whenever
Small proportion.
you slice out any part of a circle from the center, like when you're doing pizza or cake, each part that you slice and take out is known as a sector. For a pizza that is cut up into 16 parts, each part is a sector. But the key thing about sectors, the sections are sliced out from the middle, right? Now, if you take out this slice that I've highlighted with this color marker here, what you'll notice that if I take out this slice, there's still going to be a bigger slice that is left that can be shared. Is that clear? So the slice of this sector would include the slice of this sector would be what I'm using this to highlight. So we cut out all of this part here. This is a sector. If somebody take out a big slice like that, that's a sector. But when you take out that slice, a bigger portion that still remains is also a sector. But the smaller slice is known as the minor sector, and the larger slice is known as the major sector. Now, so if you're thinking of this in terms of sectors, what you realize about the angle at the center is formed at the slice of the smaller sector. You follow? The angle 2x at the center is a part of the smaller sector. Everybody see that?
Yes, sir.
Right. Now, the other angle which is formed at the circumference in the opposite sector. So if you look at this angle is now formed in the other sector at the circumference. Now, so this what is the theorem saying? It says that the angle that 2 points, so the angle that 2 points of a circle, an arc of a circle. So the angle at 2 points of a circle, and the 2 points they're referring to here would be A and B. So you have a point A and you have a point B, sorry, C. So if you form an angle from 2 points of the center of this, 2 points of the circumference. So from the same 2 points, you form an angle at the center, and from the same 2 points, you form an angle at the other sector at the circumference. The theorem is saying that the angle formed at the center is twice the angle formed at the circumference. Is that clear? Now, if we were to look at this in another way, you could imagine that from this point A, and from this point A, let's say you form an angle down here. Can you relate the theorem to this angle? And I'm going to call this the angle Y. Can you relate the theorem that we just mentioned for X? Can you relate it to Y? This angle is now formed at the circumference below the line, below the point A and C. So which angle would be twice as Y? Guys?
Sir, can you repeat because my internet is giving problem?
Did you get the theorem, what you mentioned about the theorem just now?
No, sir, because I had to come off and rejoin because I wasn't hearing anything at all.
All right. All right, so let me clear what we have here. So the theorem is saying this way, from 2 points on the circumference, A and C. If you form an angle at the circumference at B, that angle would be X. But from the same 2 point A and C, you form an angle at the center and going back to C. So the theorem is saying that the angle that is formed at the center is twice the one which is formed at the circumference. So this angle at the center is 2x. And the angle at the circumference at B would be just x, because the one at the center is 2 times the one at B. So the one at B is X, the one at the center are going to be 2X. Is that clear? Is that clear, Mr. Isam?
Yes, sir.
So that's a theorem. That's what the theorem is saying. So I'm saying now, suppose from A, I form an angle on this arc below A and C. Are you following me, Ms. Wesam?
Yes, sir.
And let's say that this angle is Y. I am asking you now, relating the theorem to this, which other angle would be 2 times Y?
Would it be if you draw the angle from upward, sir?
From here to here?
No, sir. I was looking.
Here to here?
Yes.
So what are you saying in terms of the theorem? This angle that we draw here
Would be bigger.
So what would be the size of it?
The size that 2Y, sir.
You're guessing?
No, sir.
Yes, you're guessing. Yes, it will be 2Y. So
Okay.
I really want you to understand in terms of the theorem is that if the angle that you form is at the circumference, right? If you look at this entire shape here, look at this entire shape, because I want you to kind of get this. This shape here, what that shape in red looks like.
An obtuse angle, sir. Oh, diamond, sorry.
Right, the diamond. Now what you notice in terms of the angle that is formed at the center is inside the diamond.
Yes, sir.
And that is twice it is outside the diamond at the center.
Yes.
You see that?
Yes, sir.
Do you see that, Miss Green? Miss Green, are you there? Are you hearing me? Please respond.
Yes, I'm here, but I don't understand.
All right, I'm just showing you that this shape that I've just drawn in red, right? This angle here forms within that shape, within the diamond. You see, this one from inside the diamond, but at the center. You're following? And the other angle, which is here that I draw from here at the top here, is outside the diamond. So this angle outside the diamond is the angle which is twice the one inside the diamond. You're following?
Yes, sir.
Right. So that's how the theorem works. It means the one that forms at the circumference is going to be inside the shape. And the one that is formed at the center going to be outside the shape. You get what I'm saying? Let us apply the same principle to the one within the green line. All right, so let me clear this. Now, this green line shape, you see the green line shape?
Yes, sir.
Right, the one that is at the center, sorry, the one that is on the circumference forms inside the shape. So the X angle inside the shape here is the one that forms at the circumference. Now, the one that is twice that going to be formed outside the shape at the center. You follow?
Yes, sir.
So this one at the circumference is always within the shape and the one at the center is outside the shape. If you can remember that, then you shouldn't have any problem in terms of identifying the one that is twice the one at the circumference. Is everybody following, Mr. Artie? Do you understand that?
Yes, sir. I'm getting what you're saying.
Yeah, your mic is still low, Mr. Artie.
Sir, me don't know, because the rain of fall.
Okay. So to blame it on the rain. All right, Ms. Wasom, is it clear to you now?
Yes, sir.
Is it clear to you?
Yes, sir.
Okay, good. So one of the things about circle theorem, guys, is that these theorems that you're getting individually will be compounded in one question. So they will put like 3 or 4 theorems in one question. And if you're not able to identify them separately within the question, you will become confused. All right. Now, look at this theorem. The angle subtended, or the angle forms at an arc of a semicircle. And everybody know what a semicircle is, right? What's a semicircle, guys? What's a semicircle, guys? Come on, guys.
Semicircle, no half of a circle, sir.
Exactly. So this theorem is saying that for half of a circle, the angle that is formed at the arc is half they're saying that the angle that forms in the semicircle is at right angle. That's all this theorem is saying. So any angle that is formed within a semicircle at the circumference will give you a right angle. So if you should form another angle in here on the circumference, it will also give you a right angle. That's what the theorem is saying. So any angle formed on the arc within a semicircle will give you a right angle. Is that clear to everybody? And so if you also form in this semicircle down here, you will also have right angle. Is that clear, guys? Angles formed at the arc within semicircles are right angle. Go ahead, Ms. Wilson.
Yes, sir. I'm just stating that I am clear on that.
Okay. Now, do you see anything from this theorem relating to the previous one? Is there anything in the theorem that you can relate to the one that we just looked at, guys?
Sir, to me, but what I'm seeing is that the angle at the arc would have been bigger.
No, man, the angle at the arc in all the semicircles are the same. You see, this one is a semicircle. That means it A and B go right through this.
Oh, so you're just referring to the semicircle right now.
Right. If you cut this into 2 half circles, the line AB would cut it into 2 because this card go right through the center, which is the diameter. This card is the diameter. So this half above A and B would be a semicircle. The half below would be a semicircle. So any angle formed within that semicircle going to be 90 degrees, whichever semicircle you form it within. Once it is formed at the arc, are at the circumference, they're all going to be, doesn't matter where inside there it is formed, it's going to be 90 degrees. Is that clear, guys? Now, I was asking you to see if you could relate it to the theorem before. Now, if you think of it in terms of the theorem before, what would be the angle inside the shape? The angle inside the shape would be at C, and that would be 90. What would be the angle at the center outside the shape? What is that angle, guys?
You mean the name of the angle, sir?
No. What's the size of the angle?
Sir. Sir, would it be half of 360?
What's the size of the angle, Ms. Waysome?
Would it be half of 360, sir?
Half of 360 is how much, Ms. Waysome?
Half of 360 is 180. Okay, 180.
So would it be half of 360? Ms. Waysome, I'm waiting on you.
Yes, sir.
What's your answer, Ms. Waysome?
I was saying 180, but I am not sure.
Well, if you really think about it, it is relating to the theorem before. So if this one over here is 90, the one at the center going to be 2 times 90.
Oh, so it would be the 180.
So is the same theorem that was just shortened to be a semicircle? It's the same theorem. And we know that you could even look at this and say angle on a straight line is 180. So suppose they didn't know the angle up here to be 90, right? Suppose they didn't give you this angle, but you see that this is a straight line, it's a diameter. Based on this theorem, you could say angles on a straight line, because they could just give you the question like this, you know. They could just give you the question like this. And they say, find the angle at C. Without, they would give you without this even square box in it. They can give you without the square box. And so they would be expecting you now to reason based on what you know about angles on a straight line. So angles on a straight line would be 180. So you would know that this angle is 180. And from this, you can use the theorem that we were looking at now and say the angle sub 10 at the circumference would be half of 180, which is 90. So these are the things that they are expecting you to know, guys. Is that clear to everyone? Miss Wilson, Miss Green, Miss Darty, is that clear to you? Guys, hold up your hands. Let me see. All right, good. All right, so here we have another theorem. So theorem 10 here. This theorem is saying opposite angles of a quadrilateral inscribed in a circle are supplementary. That is, opposite angles, angle A plus angle C is equal to 180. So the quadrilateral is said to be a cyclic quadrilateral. All right, what is a quadrilateral, guys? Guys, what's a cyclic? What's a
Four-sided figure, sir.
four-sided figure? Now, a quadrilateral that is inscribed in a circle would be which of these shapes?
Sir, the parallelogram.
We don't have a parallelogram here. You're referring to this. All right, let me start at B. You're referring to this one? This one?
Yes, sir.
This one? No, that's not the one that they're referring to. The one that they're referring to would be the one that is formed that is touching the circumference at every corner of the quadrilateral. This one is the one that they're referring to. So an inscribed shape, all the vertex of that shape touches the circumference. Is that clear, Miss Green?
Yes, sir.
So you could also inscribe, all right, let me see if I can draw. So suppose I have this circle and you're inscribing some shape in that. So for instance, I'm inscribing this shape in this. Then what would happen? I would have to draw this shape such that I would have to draw it such that each of the vertex or each of the vertices would have to touch the circumference at one point. So if all of these angles at the corner of the shape is not touching on the circumference, then it is not inscribed. So just to give you clarity of what we mean by inscribed. So ignore the inner lines and the lines that form the shape from point A, B, C, and D. That would be the quadrilateral that they're referring to. And that quadrilateral is known as a cyclic or cyclic quadrilateral. Now, the opposite angles within that quadrilateral are said to be supplementary. Now, so if you have an angle at A, the one that is opposite to this angle would be the angle at C. Now, these two angles are said to be supplementary. And supplementary angles, when you add them, you will get 180 degrees. So if you add the angle A and the angle C, you will get 180. So that is true for all what we call cyclic quadrilateral. The opposite angles, when you add them, you will get 180. So it means that if A plus C give you 180, it means that the angle D plus the angle B will also give you 180, because those are also opposite angles, and because the quadrilateral is cyclic, it means that these two angles are also supplementary. So the angle B and D will be supplementary angles. Is that clear, guys? Is that clear? Raise your hand. Miss Green, is it clear to you? Starty, is it clear? All right. All right, moving on. Miss Wilson seemed to have fell off the connection. All right, here are some things to note. So these are just somewhat recapping some of the theorem that we would have just looked at. Now, you would have remembered this theorem which theorem this is saying? This is talking about angles in the same segment, or if you want to say angles that touching the same arc. from the line AB. So these angles above the line AB would be in this same segment and they are touching on the same arc and hence they would all be equal to X. So we had looked at that already. If we should have angles below this segment above, then these would all be in the same segment below and they'll be touching the arc, which is the red part, red arc. And so all of these angles down here would be the same. So if one is Y, the other is Y, and so on. Now this one would be the semicircle one, which you would have seen, right? And down here now is the one where the angle is at the center. So everybody should be clear on these. So this is just a summary of some of the theorem that we have looked at. Is that clear, guys? All right, now, with all of these theorem in mind, I'm going to stop sharing this here. There are some more theorems that we have to look at.